we agreed that light either waves or particles, we call them the photons. Waves, as we agreed, is a disturbance that travels through a medium transporting energy from one location, which is the main source, to another location without transporting any matter. While photons are very small or tiny particles discrete from the light, each photon is a small or tiny pocket of energy, which means the photons represent light quantity, or we call it the quantum. The Scottish scientist Maxwell suggested that light is in fact a combine of electric wave, and perpendicular to that wave we have another wave, which is the magnetic waves. So we have two combination of light, one perpendicular to the other. Perpendicular means with 90 degrees. This is the electric one, and this is the magnetic one, to form the electromagnetic waves of the light. Electromagnetic waves of the light. Light considered as energy. And the energy all the time means the ability to do the work. Ability to do the work. We have two kinds of energy. They could be potential or kinetic kind of energy. What's the difference between those two? Potential energy means it's a station kind of energy, which means it doesn't move. The energy doesn't move. While in kinetic energy, it's moving kind of energy. So, since light is moving photons or moving waves, that immediately means light is kinetic kind of energy since it's moving. To understand the idea of potential and kinetic, let's say we have two balls, for example, balls number 1, balls number 2, above a table. In potential energy, this ball will remain here without moving. So this is a stationary position of the ball, its potential energy. But when the ball moved down, fell down, this movement is the kinetic energy, which is the movement of the ball. Kinetic energy, the moving kind of energy. Light, again, is the kinetic kind of energy. And in energy, we have a law that says energy cannot be destroyed nor created. So how can we take energy? We can change it from one shape to another shape, or change it from one form to another form. What about the light? Can we destroy it or create it? Since light is kind of energy, type of energy, we cannot destroy it or create it, but we can change it from one form to another form. The main sources of the light is the sun, which is the natural source of the light energy. We also have artificial kind of sources. Artificial such as bulb, such as LED. In the sun, the natural source, we change the nuclear energy into the light. In the sun, a very high temperature combine one hydrogen to another hydrogen to form the helium. This will give a very high source of energy, which is the electromagnetic waves or the light. While an artificial source of light such as the bulb or the LED, we change the electrical energy into the light. So we don't build a new light, we don't create a new light, we change it from one kind of energy to another kind of energy. When we have the light from the sun, this light will reach the atmosphere and the earth. We have the plant on the earth. They will capture the light, change it again from the light energy into chemical energy. In a process we call it the photosynthesis, which means we changing the light again from this form to another chemical form. In a process we call it the photosynthesis. Here we change the light into chemical compound, which is the glucose. Light is kind of kinetic energy because it's moving in waves. And we have two types of waves. One is transverse, while the other one is longitudinal. This one, the particles move in perpendicular to the wave direction. While in longitudinal, the particles move parallel to the wave direction. Parallel means the two lines can never meet. They both move in same direction, one parallel to the other. They will never meet. While perpendicular means one line at the 90 angle of the other line. In transverse waves, this is the direction of movement, but the waves move in this way, up and down, perpendicular to the direction of movement. In parallel kind, this is the direction of wave movement, and the waves move at the same direction parallel to the direction of the wave. Light waves are transverse waves, which means they move in perpendicular to the direction of movement of the wave. Light is transverse. So light is kinetic energy, moves in transverse waves. We can look to the video to see the difference between longitudinal waves and transverse waves. Here the particles move at the same direction of the movement, while in transverse, the movement in this direction, while the particles go perpendicular to the movement. Light energy has many properties. The first one is intensity. Let's say we have source of light. The amount that the source of light emits the light, we call it the intensity. Is it a lot of light or a small amount of light? The rate of the light emits from the source per unit area is the intensity of the light, and we measure that in watts. The other one is the cycle. This is the direction of movement for the wave, and those are the waves. In the wave, we have peak, which is the top of the wave, or we have trough, which is the bottom of the wave. Between one peak to the another peak, that's a complete cycle. So the wave will keep repeat itself. That's another one, and that's a third, and so. So from peak to another, this is one cycle. From this peak to the third peak, that's the second cycle. While frequency means the number of cycles pass through a specific distance in limit time. So we have a specific distance and specific time, let's say 1 second. How many complete cycles do we have in that distance per 1 second only? So frequency is numbers of complete cycle in a specific distance for a period of time. This one we measure it by hertz or Hz. We also have the wavelength. This one is the distance between two peak or two trough. Two peak or two trough. And we measure it by meter or nanometer. Nanometer immediately means 10 powered by minus 9. And the wavelength had the symbol lambda. So between two trough or two crest or two peak, we have one lambda, one wavelength, and we measure it by meter or nanometer. Lambda. The distance between two peaks or two trough. We also have the period. The wave period means the measure of the time it takes for the wave cycle to complete. So the time that the wave need to complete one cycle, and we measure it by second. And it's the inverse of the frequency. We have velocity too. Which means the rate of travel or the distance the wave will travel in a specific time. Since it's a distance, we will measure it with meter per second. So, how many meters that wave can pass through 1 second. In vacuum, which means empty area without any gas, without anything, the light and electromagnetic waves travel at 3 times 10 powered by 8 meter per second. That's the speed of the light in vacuum, because in most other media, wave velocity is slower than in vacuum because light interacts with other materials, refraction, reflection, which slow the speed of the light down. So in vacuum, the light or the electromagnetic waves is faster than media. And you should remember, waves of electromagnetic is the only kind of waves that can pass in vacuum. The others, such as sound waves, cannot pass in vacuum. We also have the amplitude. Which is the maximum displacement of the vibration of the waves. We have peak and we have the trough. Amplitude is the maximum displacement that the wave can reach. It could be in positive in peak or negative in the trough. The velocity, frequency, and wavelength are related by this equation. The relationship between velocity, frequency, and wavelength are related by this equation. Velocity equal the frequency multiplied by the wavelength. The frequency and wavelength are inversely proportional, which means when the wavelength increase, the frequency decrease, and vice versa. When the wavelength is small, the frequency will decrease. So they are inversely proportional. And if you can remember, we said here in period, it's the inverse of the frequency, which means frequency here also equal 1 over time or the period. Let's have an example for that. The wavelength of sodium in vacuum is 589 nanometer. What is the frequency of the Na source in the vacuum? We know the wavelength lambda is 589 nanometer, and we also need the velocity of the light or the speed of the light in the vacuum. V equal 3 times 10 power by 8 meter per second. And we need the frequency. We said velocity equal F frequency multiplied by lambda, the wavelength, which means F equal velocity over the wavelength. inverse relationship with the wavelength. So F will equal 3 times 10 by 8 meter per second over 589 nanometer. The units are not compatible. We need to transform the nanometer into meter. Nanometer means immediately 10 powered by minus 9 meter. And now it's meter. So again, substituting into the equation, frequency equal the result will be 5.09 10 powered by 14 hertz. Another equation we have that velocity or the speed equal the distance over the time, meter per second. So we have that image at 0, and those are the frequencies. Here is 5, here is 10, here is minus 5, and here is minus 10. So that represents the amplitude. This is the amplitude. This is the distance, so it's by nanometer. That's 0. Let's say we have 50 here, 100, 150. If we want to measure the amplitude, the maximum displacement here is 10. So that's the amplitude. What about the wavelength? The first peak, if you see it here, is about here 25. And the next peak is here, which is about 125. The distance between this peak and this peak means 100 nanometer. So that's the wavelength. Can we calculate the velocity or the speed from this picture? If we count the cycle, which means how many times the wave repeats itself, this is one repeat, this is the second repeat, and 3 and the fourth repeat, which means 4 times. And we have the wavelength 100 nanometer. So 4 times 100 nanometers, that's 400 nanometer in this diagram. Let's say the wave path this diagram in about 2 multiply by 10 powered by minus 15 seconds. Can we find the velocity from those components? Well, we have the distance 400 nanometer and we have the time. We can use this equation to resolve the problem. So velocity equal distance, which we have it here 400 nanometer over the time, 2 multiplied by 10 powered by minus 15 second. And again, we need to convert the nanometer into meters, so multiply by 10 powered by minus 9, which means the result, the velocity will be 2 multiplied by 10 powered by 9, powered by 8 meter per second. All of those properties and characteristics work for all of the electromagnetic waves. Again, electromagnetic waves means combination of electrical field or electrical waves and magnetic field or magnetic waves. And this one noticed by Maxwell. So Maxwell, the one who said light is electromagnetic waves. So we keep saying light and electromagnetic waves. If there is any difference between them, in electromagnetic waves, we have two parts. One that you can see by your eyes, one that you can detect it by your eyes, and you use it to observe and see, and we call that the visible light. So light is part of the electromagnetic waves. The other one that you cannot see by your eyes is non-visible electromagnetic. And that electromagnetic waves have a different wavelength, starting from almost zero until infinity wavelength. If we see the picture, you'll notice that the visible light is a very small part of the electromagnetic waves. The wavelength that you can detect it by your eyes extend from about 400 nanometer, which is the violet color. So violet is the short part of the visible light. Quite the opposite is the red color, which is the long part with wavelength about 700 nanometer. Shorter than that or longer than that, your eyes cannot see it, and those are the non-visible electromagnetic waves. They could be really short, such as in gamma, have the size of atom, or like really long, which had the size of building. The visible part, of course, we use it to make things able to be seen. It's also help in the photosynthesis, building vitamin D inside your skin, and others. The ultraviolet one, which we cannot see by the eye, immediately after the violet color. This one could cause cancer, and we absorb it by our skin and our crystalline lens inside our eyes. We use the ultraviolet in fluorescent tubes. They could also use it in killing germs and bacteria. The X-ray, I believe you heard that name before, we use it in medication for imaging. We use it for imaging. Gamma rays also we use it in medication to kill the cancer cells. The long part of the electromagnetic waves that we cannot see starting after the red color, which is the infrared. Infrared, we use it in heaters to transmit the heat. We also use it in a special kind of glasses so we can see at night. We also use them in the TV remote control. The microwaves, from the name, we use them in the microwave machine to cook, also in radar, telephone, and different signals. The very long one, which is the radio waves, we use them in broadcast, meaning in radio. So So radio and light waves are similar. Both are electromagnetic waves. Here in optics course, mostly we're going to talk about the visible light and its behavior. Again, the section of optics that deals with the behavior of light and its wave characteristics is the wave optics. Or also the physical optics. So physical and wave optics is the study of the light behavior and different phenomena of the light, such as diffraction, interference of the light. And there are many theories in the wave optics. Most importantly, the Huygens wave theory, Young's experiment, wavefront and wave normal. Huygens proposed this wave theory of light, and his theory was able to explain many phenomena like reflection, refraction, interference, and even diffraction of light. But it failed to explain the polarization. So Huygens' theory explained the refraction, reflection, interference, and diffraction. We're going to explain each one of those during this course. But unfortunately, it failed to explain polarization and some other different behavior in light. So what is Huygens' theory? It states that all points in the wavefront are secondary source for light. For example, we have here a source of light. This is the primary source, the main source of the light. So here we have the points of the light. So according to Huygens theory, each one of those points is a secondary source of light. So this light will spread like that around this point. So this will transfer the light into another line. In the other line, we also will have those wavefront. This is again will be a source for the light here, and this one will be a source for the light here, and so until it reach this point. Here it will be the source for light again here to separate the light in this direction again. This one will be a source for this point, for this point, for this point, for this point, and each one of those points will spread the light for the next point. Each one of those wavefront is the secondary light source for the next point. But what is wave front? Wavefront is an imaginary surface that we draw to represent the vibrating part of a wave. So it's imaginary, it's not something real. But we use it to explain the idea of vibration of the light or the waves. And we have three types. The first one is the spherical wavefront. And here our wavefront in the middle. The waves of light around it will spread in spherical shape. In different directions. And again, this one will be a source for a point here, and this one also will be a point to another one here, and so. The spread of light, we call it the propagation. Propagation again means the spread of light. The second one in the wavefront is the cylindrical wavefront. In cylindrical wavefront, we have beam of light, that's the light, it have the cylinder shape, that beam has a cylinder shape, so the separation of light will be like that, from this direction so cylindrical wavefront form when we have a linear source of light. The last one is the plane wavefront. This one occurs when the light is coming from a very far source. So the wavefront now are parallel. So the wavefront now are planar. Beside the wavefront, we have also something we call it the wave normal. The wave normal means when we have wave front and any kind of wavefront, spherical, cylindrical, and we have a perpendicular propagation of light. So this is the wave front. Here we have light, and we have another source of light but perpendicular to the wavefront. Then this one we call it the normal wave or wave normal. Back to Huygens theory, who said every wavefront is a secondary source of light for the next point or for the next wavefront. So this one will be a source for this one. And either this one will go as a source for the third one and go on. When this is the main source, we will call it wave front. Again, it's something imaginary. And this one here will be the wavelet. Then again, this one will act like wavefront for this to be the wavelet. This one will act as wavefront for this one, which will be the wavelet for this one. Again, this is the source, the main source will move as waves, and each wave contains wave front. Those wave front will be a secondary source of light for the wavelets. Here, those are the wavelets who will again separate the light to the next wave. Young also explained almost a similar idea about the waves. He did an experiment by using a source of light. He did an experiment, we call it the double slit experiment. He brought a source of light and put a barrier, an opaque barrier with two slits or two openings. The light will move in this direction and then will pass through these openings. This experiment proves that light is really wave. When those waves of light meet a gap or an opening in a barrier, they will move through this tiny opening in a phenomenon we call it the diffraction. So when the light is spread from very small or tiny opening, we call that the diffraction. The spreading of the light in diffraction depends on the width of the gap, or the opening compared to the wavelength. which means if we have the gap much larger than the wavelength, the spread then is small, not that big. If the gap has almost the size of the wavelength, this will cause a lot of spreading. So comparing to the size of this and this is not much big, but here the difference is really big. So small gap or gap have the same size of wavelength. This will cause a lot of spreading. If the gap larger than the wavelength, this will cause a little spreading. If you notice in young experiments, when the waves of light pass through those gaps or opening, the waves coming from the first gap overlap waves coming from the gap number 2. So overlapping here, for example, overlapping here, here, and here. This overlapping, we call it the interference of the light. So passing of waves through this opening or those gaps is the diffraction, and overlapping of waves is the interference of the light.